All right, in 14.5, we're going to look at temperature and how that affects our reaction rate. We're also going to look at some activation energy and what that is, and talk about how we determine activation energy using an equation and some graphs. So the first thing we're going to start off here with is just a little bit about temperature. Okay, and we talked about earlier that the rates of your chemical reaction will increase as my temperature increases. Think about if I want to make pizza dough or something. Okay, that's going to rise a lot faster at room temperature than in the fridge. And then the opposite works for things like mold. Okay, if I want something to not go bad as quickly, I will put it in the fridge to slow down that reaction rate, that molding reaction. Okay. The faster the rate at a higher temperature is due to this increase in the rate constant with an increasing temperature. All right, and now we're going to look at what we call the collision model. Okay, which is just talking about pretty much what it sounds like, molecules colliding. Okay, the molecules must collide to react. That should be a kind of a duh. Okay, they can't react if they can't combine. So the greater your number of collisions per second, the greater the reaction rate. So as my concentration goes up, I have more in there. I have more collisions, I have more rate. As my temperature goes up, they move faster, they have more collisions, they have more energy when they collide, so they're more likely to stick together. I'm going to have more rate. If I only have a small number of collisions, I'm not going to have a very fast reaction rate. So only actually a small number of collisions result in a reaction. Just because they collide together doesn't mean that they are oriented correctly or that they have enough energy to actually make the reaction and stay bonded together. So even if they do collide together, they don't always actually even make the reaction. So you have to have a ton of collisions just to have a few of them to actually make my reaction. Okay, so we have a picture there on your notes, which is looking at my collision and my orientation. Okay, I have a before collision, they're apart, then they collide, and thereafter I have my actual reaction happen, they separate. If you have now before, now they collide differently, now I have a different after. So it's all about actually how they are oriented. Okay. In order for my reaction to occur the way I want it to, they have to be oriented in a particular way. The sides that are going to bond need to be the ones that actually collide. So not only do they have to collide going the right way, and they have to collide with enough energy. If they don't have enough energy, they might just bounce off of one another and not actually ever collide. Okay, and that has to do with our next thing, which is our activation energy. Okay, activation energy deals with the energy, how much energy it actually takes to get the reaction to occur. So like I just said a second ago, the collisions have to actually have a certain number of energy to react. And the energy comes from the colliding molecules, and it's used to then stretch the bonds, break the bonds, and then actually make my reaction happen. Now this activation energy is just what it sounds like. It's the energy required to activate the reaction. So it is the actual minimum energy that I need to get the reaction to occur. Because what happens is my molecules require a minimum amount of energy, a set number that those molecules have to have before they want to break apart or stretch apart and actually cause the reaction. Okay, there is a barrier that exists to have a molecule form as an unstable intermediate. And so when we look at this picture down here, okay, this is where I start with down here on the lower left. So my reaction pathway means this is my reactants here to start, and this is my products here at the end. I have to get this certain number of energy here, get over the hump, before I can actually then cause my reaction to happen and make my products. This middle thing we call here is our activated complex. And activated complexes are also known as intermediates. They're usually unstable intermediates, ones that don't last very long. Okay, it's kind of how the molecules are shifting when they're in between being together and then being apart. So I have each molecule here on the left, and then they kind of bond together in kind of an interesting fashion to make an intermediate. They need so much energy to make that intermediate, and then when the intermediate is made, it can then break apart or move a little bit, I guess, to make the product that I want. Okay, and this EA in your drawing will be a little bit clearer, is from the top of that hump there to where I start. Now this is not towards the bottom, but right here, my EA is my activation energy. Okay, it's the energy to activate or get the reaction to actually go. So those sentences there are what I was just saying about the energy getting put into the rotate, twist, or break bonds, and you form that unstable intermediate or that activated complex. Now we're talking about the rate with our activation energy. There's only a couple more things you got to put in here. You're running out of room. Okay, now the rate depends on the activation energy. Generally, the lower the activation energy, the faster the rate, because that means the least amount of energy I have to put into it to get it to actually go. Now the reverse reaction, okay, you have to kind of start with my products and go to my reactants. And that's very similar to going the other direction, but now my activation energy is different. Because see this bottom part here in the red, that's the energy, okay, that I would actually get out of this reaction when it occurs. That would be a negative number, okay, because I get energy back out, okay, because my energy when I'm done is lower than what I started with. So if I wanted to go back this direction, my activation energy would now be this plus the amount of energy. I have to put all of this energy to get back up here, go back over this hump. So this reaction is not very likely to go back the other way because it actually takes more energy to get it to go that direction than it did to get it to go to the right. Okay? And again, this reaction is exothermic because my product is lower than my reactant. Alright, now we're going to talk about the Arrhenius equation, which deals with my activation energy. Okay, most reactions, my rate goes up as my temperature goes up, but it's not an actual linear relationship between the two. Okay, there are three factors that actually go into this, talking about my temperature and my rate. And they are the number of molecules with my activation energy, the number of collisions per second, and the number of collisions with the correct orientation. And this gets all put into one equation that we're going to look at and just talk a little bit about if I actually want to figure out my activation energy. And we end up with this equation that actually looks like this. And I had my K equal a big uppercase A. I have a little e, which is actually that E constant. Then I have negative EA divided by RT. And this is called the Arrhenius equation. Okay, K, the lowercase k, this is my rate constant for the equation. A is a frequency factor. This is nearly constant. So oftentimes you kind of ignore it. E is that E button on your calculator, the lowercase, not the big E with the times 10 to it, but the lowercase e, which has to do with, I believe, natural logs. EA, that is your activation energy. And then I have T, obviously temperature, and R. Now this R is our 8.314 joules, not the 0.08206, because this one is dealing with energy, which deals with joules. So if I wanted to figure out my activation energy, you have to do a little bit of messing around with the equation and rearranging it to actually solve for EA. Okay, but as my activation energy increases, my constant decreases because not as many molecules possess enough energy to react, so my rate goes down. Which makes sense. Okay, now we're going to consider a series of reactions here in this next problem. Okay, and it says they have the following energy profiles, which just means that how the energy changes as the reaction goes forward. So it says rank their reactions from slowest to fastest, assuming that they have nearly the same frequency factors, meaning kind of how often they collide. All right, so I want to know how fast they go, slowest to fastest. Well, activation energy, that would be these numbers here. Because I don't care about the total, I just want to know how much energy it takes to get over that hump. Well, that's going to be just looking at the activation energy. So the slowest one is going to be the middle one. The next slowest is going to be this one, and the fastest is going to be the first one because that's the number, that's the order that those numbers go in. Now if I wanted to go on the reverse reaction, meaning I wanted to go this way on all of these, okay, now I'd have to add in those 5s or those 15s or those 10s. Okay, well the reverse reaction, I'd have to put in 15 here because it's 20 and then 5. I have to put in 40 here. I have to put in 25 here. So my reverse order reactions would go 2, 1, 3. If I want to go back the other way. Okay, now if I was going to determine an activation energy, this gets to be a little bit more crazy. You take the natural log of your Arrhenius equation. And what we end up with looks something like this. The natural log of K equals my negative EA over RT plus the natural log of A. So if I graph the natural log of my K versus 1 over time, our temperature, I'm going to get a straight line. Because this is going to be my Y, this is my M, 1 over T is my X, B is my Y-intercept. Okay, so if I could graph that, I could look at the slope of that line. So I would have natural log of K, and then I would have 1 over T. I'd graph it, okay, and my slope would be equal to negative EA over R. And I could very easily then figure out what my EA would be because R is a constant and I would know the slope of my line. Now, if you were to have different rate constants at different temperatures, if that was the information they gave you with a bunch of rate constants, there's also an equation to help you figure that out. Okay, and it is the natural log of K1 compared to the natural log of K, the other K constant, equals EA over R times 1 over T, the second one, minus 1 over T, the first one. These are not things you really have to memorize. They should be given to you. Okay, so the last thing we're going to look at is a practice problem. It says the following table shows the rate constants for the rearrangement of methyl isonitrile at various temperatures. From these data, calculate the activation energy for the reaction, and I want to know what is the rate constant. So what I would do here, and I'm going to give you some of the numbers, is I'm going to graph it. All right, and I'm going to graph the natural log of K and 1 over temperature, because I should get a straight line, and I'll get my slope. Well, 1 over T is going to look like 0.00216, 0.00212, 0.00199, and 0.00191. The natural log of the constants is going to be negative 10.59, negative 9.86, negative 7.37, negative 5.76. You can just plug them in your calculator and get your slope of your line, or you can take the beginning and the end, take this value and this value, or sets of values here, and then change in Y over change in X, get my slope. You should get a value of about 19320 is what I had. Okay. Now if I have that value, then I'm going to solve for my activation energy. So my slope, my 19320, is equal to my negative at my activation energy over 8.314. And I'm going to get a really big number of joules, which is going to be 160626 joules. I'm going to divide by 1,000 and just make that about 160 kilojoules. Okay? And that's actually kilojoules per mole, because when you deal with the R constant, it has mole in it. So that is my activation energy. It takes that much energy for every mole. Okay? Now B gave me, or wants to know the rate constant value at 430 Kelvin. So I have a whole bunch of other stuff, and I need to figure out the rate constant at a particular temperature. So that is that second equation we were looking at. Okay, that's the whole natural log of the K. I'm going to do that as the K I'm looking for. Over, I'm going to go 2.52 times 10 to the negative fifth. I just picked the first one. Okay, equal to my activation energy, which is 160,000. Over my 8.314 times 1 over 462.9 minus 1 over 430, which is the temperature that I am looking for. I get all of this lovely math. Then I'm going to get rid of my natural log. I take E to the both sides. So I'm going to take E to whatever this huge number, not huge, but whatever that number there is going to be. And it's actually negative 3.18. So I have K over 2.52 times 10 to the negative fifth equals E to the negative 3.18, and I'm going to get an activation, a rate constant, of 1.0 times 10 to the negative sixth, and then second to the negative first, because that's what the rate constant value was for all the other ones.